Well, hello there, good people. Today we are going to be talking about motion graphs and interpretations. Hey, you remember back in your childhood when your math teacher put an equation on the board, something like this? Let's do this one. And your teacher asked, hey, how do you graph this? Well, now you would look at that and you would say, well, I know that that's a line, and I know that it has a slope of 2, and I know that it has an intercept of 1. But before that, back in the day, what you did is you started by making a table. Do you remember this? You would start with a little table here and you would say, okay, here's my x variable. If I plug x into y, then I get this one. And you would put in some points here. You would say, okay, let's start with 0. You'd say, when I plug in 0, in for x here, I get 2 times 0 plus 1. That means that my y ends up being 1. Then you said, okay, let's try another thing. Let's try 1. And you said, okay, when I plug in 1, I get 2 times 1. That's 1, or that's 2, plus 1, that's 3. And you'd plug in a 3 here. And then you'd say, okay, let's try the number 2. And you'd say, okay, 2 times 2, that's 4, plus 1, that's the number 5. And so on and so forth. And you would get something like this. And you would keep on doing this here until you got a good number of points. And then once you had a good number of points, you would create a graph. And when you create a graph, what you would do is you would say, okay, here's my y-axis, and here is my x-axis. Well, right here, this is my y-axis going this way. You would say this is my x-axis going this way. And you would plot each of your points. You'd say, okay, 0 is at 1, and then you'd say, okay, if I have 1x, that's 3y, and you'd go up here like this, and then you say, okay, if I have 2x, that's 5y, so 1, 2, 3, 4, 5, and then you'd say, okay, and if I have 3x, that's 1, 2, 3, that's 7y, like this, and then you would say, I have found a graph, and you would create a best fit line that would be much better than mine because it would actually trace through your points. You would say, wow, that's so cool. This is all old news from back in the day. Now, you also remember, sorry, I'm getting all perfectionistic about this, and I really just need to leave it. Leave it, it's fine. Okay, that's good enough. Hey, by the way, isn't this exactly what you're doing in your lab? Don't you have some points on your x-axis and other points on your y-axis, and you're plotting these points, except in this case, your x-axis isn't x, it's time, and your y-axis isn't y, it's displacement, and then on your second graph, it's velocity. So you put your different variables on your different axes. Well, hey, do you remember back in the day, if you actually wanted to find the slope of this graph, this is how you would plot your points. But then if you wanted to find the slope, what you would do is you would choose 2 points on this graph. You remember this from your childhood. You choose a point right here, and you'd say that one looks good. Oh my, okay, let's all just relax here. Relax. Can we undo that? Is it going to let me undo it? Maybe, but maybe not. Okay, let's try my eraser. Oh, wait, just kidding. We're good. We're all in the clear, people. Worry not. Okay, so you choose one point right there, and you choose another point right here. Points that you're good about. And then you would say, okay, if I take, did I choose a point? I tried to choose a point. I really, really did. Hello? Hello? It says no squiggles for you. Undo. Undo. Hello? Hello, are you saying that I would like a marker? Is my mouse even working? Okay, sorry everyone. Why is this not working? This is really, not going well for me. Do none of my pens work? Is it the color purple? Do you just hate the color purple? Is that the issue? Okay, one second. Let me see if I can get my pens to work. I'll be right back. Oh gosh, did we even pause this video? Why is this taking so long to figure out? Okay, perfect. So you'd make 1 point up here, you'd make another point down here. Then you would say, okay, this point lands at a certain position on the x-axis. And this point lands at a certain position on the x-axis. And this point lands at a certain position on the y-axis. And this point lands at a certain position on the y-axis. And you would call this something, wow, that is really very bad. You would do better than that. But you call this something like x1, and you call this something like x2, and you call this something like y1, and you call this something like y2. And then the part where you have to make the slope, you'd say the slope, and you would use the letter M to represent slope because, of course, that is the most logical choice. And you would say that the slope is equal to rise over run. And you would say, what do you mean by rise over run? And your teacher would say, well, by rise, I mean it's your change in y. And by run, I mean it's your change in x. So what you do is you do y2 minus y1, because that's your final y minus your initial y, all over x2 minus x1, because that's your run. It's between your finish point x2 and your starting point x1. And that would give you delta y over delta x. And that would be your slope. And you said, oh, yes, very wise. Thank you very much, good, kind teacher. And your teacher would teach you all those things. And that was part of your childhood. Well, now, on the graph that you made on your lab, you didn't do x and y here. What you did was something totally different because you did distance and time data. And on your distance and time data, your graph looks slightly different because instead of a y here, boop-a-doop-a-doop, and instead of an x here, boop-a-doop-a-doop, and these are not x's and y's, and these are not, I really should just erase this whole thing. Okay, wait, let's speed erase the whole thing. Upgrade to supersize. Yes. Now let's knock out this whole graph. Bye, graph. It was nice knowing you. You were helpful to us for but a moment. Oh gosh, okay. Okay, great, mass destruction. Now, here's what happened to you. Let's go blue. On your graph, are we here? Are we all like tracking along? Doesn't look like I'm on the marker mode. Okay, on your graph, you were graphing two values, time and position. That was one of your two graphs. So on this graph, you put delta t on this axis, and of course you labeled it with seconds, and then you labeled all your points here. On this side, you labeled this velocity, your position. We'll go with your position graph. You labeled this your position, and you said, yes, that is my position in meters, like this. Then you had your x variables and your y variables in a table on your lab, and it had all of your total distances and all of your total times right next to each other. And so then you made a little graph, and you had you graphed all of your little points, so you had something that looked kind of like this. And you said, okay, well that looks quite excellent. And then your next job was to draw a best fit. And so you drew a best fit of this graph. Wait, actually, let's go with this color. It's too late. Okay. You drew a best fit of your graph, and your best fit looked something like this. But pretend I did it better. And then here's what you did. Check this out. Suppose that you looked at this graph, and suppose that you chose, just like last time, suppose that you chose 2 points. Suppose that you chose a point here, and suppose that you chose, oh my gosh, why are we wreaking mass havoc? Let's try again with my undo button. Yeah. Oh no, I got the working symbol of death, which sometimes means it's gonna work, and sometimes means it's not gonna work. Okay? Also, I don't know how I ended up with like super purple right there. Okay, there we go. There's one little dot. And here is another little dot. Now let's say that I asked you to find the slope the same way that you did old style. Old school style, what you would do is you would say, okay, well I know that my slope is equal to my rise over my run. That's what I learned. You would choose 2 points. You would say, okay, well this one here lands at some time, and this one here also lands at a time. We'll call this one, it lands at some like initial time, and this one it lands at some final time. Oh, there's a bell. And then you said over here on my x-axis, this point lands at some value of x. We'll call it some like final x, and this point lands at some initial x like this. And you'd say, okay, I could do my rise over run. Sure. But this time instead of y2 and y1, I would have x final minus x initial all over t final minus t initial. And then you would say, well, hang on a second. That is really just like a final minus initial. I could squish that down and call that a delta. And I would get a delta x over a delta t. And all of a sudden, the gears inside your brain would start turning because you would say a delta x over a delta t. That's so funny. I just feel like I've seen a delta x over a delta t before. That is just so very interesting. Where could it have come from? I wonder, what is this delta x over delta t? And then you remember that delta x over delta t is speed. And this, ladies and gentlemen, is the biggest point of the day. Are you ready? The biggest point of the day. If you take the slope of a position versus time graph, you get velocity. The slope of a position versus time graph is velocity. Like, that should be a sentence that just rings in your brain and sinks down deep into your heart, where it makes you feel warm and fuzzy inside. The slope of a position versus time graph is velocity. So you can look at a position versus time graph and it tells you all kinds of things. It tells you a story about where the car has been, but it also tells you a story about how fast the car is going, because you can look at a slope and find out how fast that car was going based on the slope. Let's go ahead and take a look at an example. Please open up your textbooks to page 75. I'm going to get a new little piece of paper opened up here while you're flipping to page 75. Bum, 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 bum. Look at page 75. Isn't it great? Okay. On page 75, do you see where it says short response on the page? Here, I'll show you. If you're on the right page, it should look something like this. And do you see this section where it says short response? Wait. Whoop. Do you see this section where it says short response? We're going to look at number 11 here on this page. So this is... This is page 75. Number 11. Okay, page 75, number 11. Yay. We're going to try B together, but let's start by reading the problem. It says, the graph below. You have to have your page open or else you're not going to be able to see the graph, and that's going to be like highly, extremely problematic. Okay. The graph below shows the position of a runner at different times during a run. Use the graph to determine the runner's displacement and average velocity. And we're going to try B, where it says for the time interval from t equals 10 minutes to t equals 20 minutes. Okay. You should be looking at this problem right now. Okay, here's what we have. Sorry, I just want to make sure I'm looking at the right thing on the problem. Okay. So we're looking for the runner's displacement and average velocity. Well, in order to do this, I'm going to start by writing down what I'm looking for. My time interval, it tells me, I'm looking for between my initial time, which is 10 minutes, and my final time, which is 20 minutes. Then, I'm trying to find both the runner's displacement and the runner's velocity for that time interval. It says I'm looking for the average velocity for that time interval. Okay, let's see what we can do. First, I'm going to start by looking at my graph here. I look at time t equals 0, and now see what my position is. At time t equals 10, which is my initial time. And now see what my position is like. If you trace up on that graph, do you see that the position is like slightly less than half of 2, or than 2.5? Everybody see that? Slightly less than 2.5. So I'm going to say that my x initial is going to be 2.4 times 10 to the third meters. Now, the book is not very clear on direction here. That's a times 10 to the third, by the way, because do you see how it says that the position is times 10 to the third meters off to the side? Okay, so 2.4 times 10 to the third meters. Now, the textbook is not very clear on direction here. So I'm just going to call this a few things. Either, if you wanted to say that this is in the positive direction, you could just use a positive sign here to indicate the positive direction. But you could also say something like forward, which is how I'll talk about direction. Okay, then let's find our final position. This is the runner's position at our final time, which is at 20 minutes. You look at that graph here, and you see that the runner's position at 20 minutes is like slightly less than 4. Interesting. I'm going to call it 3.8, but that is, again, slightly up to interpretation because of how you read the graph. I'd say you should be in the correct ballpark range, though. I go with 3.8 times 10 to the third. I'm going to say that this is forward once again to include my direction, or you can use a little positive sign like that. Okay, now, first I'm going to find my displacement. To find my displacement, well, that delta just becomes an x final minus an x initial. So this part of the problem is not too tricky. I start by writing my original equation, then I do my final, which is positive 3.8 times 10 to the third meters, minus my initial position, which was 2.4 times 10 to the third meters. Notice I'm plugging these positives in here as my direction. Then when I do 3.8 minus 2.4, then I get something like positive here, 1.4 times 10 to the third meters. If I ended up with a negative sign here, that would mean that, for my final answer, that would mean that my runner was moving backwards because my runner would start further away from the start line and end closer to the start line. Okay, so there's our displacement. Good to go. That one was almost like easy peasy. Let's check the next one. Next, we're looking for our average velocity. To find our average velocity, I know that the slope of a position versus time graph is velocity. So I'm going to start with a statement, and you need the statement in order to earn the point. I'm going to start with a statement that the slope of a position versus time graph is velocity. Then I can say that that is going to equal my rise over my run. It's going to equal, and you can write this either way. I'm okay with either way on this. Either delta x over delta t. If you want to start there, that's great. But eventually, you have to get to a step where you break that down and you say that is an x final minus an x initial all over a t final minus a t initial. The reason why you have to get to this step for me, and actually I think I'm rethinking like how I give points on this. I might give points for saying that V average is equal to delta x over delta t and then give a point for breaking it down this way, but I think this step is kind of optional here, is my thought. So let me go back and double check how I give points on that. But, so this step here, the reason why this step I know is a non-negotiable, the reason why I know that you have to have this step is because you have to get, before you plug in any numbers, you have to get an algebraic expression in terms of your givens. Notice that I wasn't given a delta x, and I also wasn't given a delta t. I was given a t final and a t initial. I was given an x final and an x initial from the graph. And so I have to get this in terms of things that I was given, which is a final and an initial. Once you have it in terms of things that you were given, then you will plug in those numbers here. Notice, I am not plugging in my delta x. I will never plug in a number that I already found into another part of the problem, because if I made a mistake up here and I plug in that mistake, then I have 2 mistakes. But if I just go back here, then I might only have 1 mistake. So you don't plug in this number, you do plug in these numbers. So we plug in positive 3.8 times 10 to the third meters. Oh gosh, I'm going to need to move my face. Face, go away. Oh, face, go away. Okay. That's pretty good. Okay. Positive 3.8 times 10 to the third meters. Let's give myself a little extra space here. Come on, you can do it. To the third meters minus my x initial, which is positive 2.4 times 10 to the third meters. Notice that I'm always including direction. Oh, whoops, my third just got blended into my 10. Notice that I'm always including direction. I'm just including it in the form of a positive sign. But if you wanted to use forward instead, then you could just write out the word forward. And that is also totally great. All over, oh, that was a terrible fraction bar. Let's try that one more time to give myself a little bit more room. All over, that's not too bad. Okay. 20 minutes minus 10 minutes? Oh, gosh. That would be giving me my final velocity in terms of meters per minute. And oh my GOSH, I'm seeing a serious problem here. So we're going to do a quick unit conversion. Before we plug in here, I'm going to go. I know that there are 60 seconds in 1 minute. I know down here I got 60 seconds in 1 minute. And I'm running out of space here. But I'm going to write it down. I'm going to write it down here all squishy times. Okay, so 10, that gives me 600. Keep 3 sig figs here. 600 seconds. And double that because it's 20. That's going to give me 1,200 seconds. Now, I'm not going to actually change my sig figs here. I'm just going to remember from up here that I preserve 1 decimal place. Otherwise, it's going to get really messy really fast. So, I'm going to go 1,200 seconds, 1,200 seconds, minus 600 seconds, like this. Plug it into a calculator, and normally you would do the step below, but I ran out of room. You always show your work vertically in this class, and you would get, let's see, we'll keep 2 sig figs at the very end here. So we'll get 2.3 meters per second. And now that is not enough because we also need direction. So we will say that that is in the forward direction. And then we are all good to go here. That is my average velocity from 10 minutes to 20 minutes. Notice how I used the slope of the graph in order to find it. Okay, that is how to find the average velocity over the interval. Now you'll remember something that's true is that not all V's are created equal. So already you've seen like V initial and V final not the same, and also V average not the same, and that's not the same as your instantaneous velocity. If you wanted to find your instantaneous velocity, that's your velocity at an instant, you would have to find the slope at a very specific point. Take a look at page 75, still same page. Page 75, number 11. Here's what I want you to take a look at. Suppose that I asked you to find the instantaneous velocity at 15 minutes. If I asked you to find the instantaneous velocity at 15 minutes, what would you do? Well, you would have to find the slope at 15 minutes. To find the slope at 15 minutes, a lot of students will do something very, very wrong. Here's what some students will do. Some students will say, okay, let me find the slope at 15 minutes. And they trace it up and they say, okay, 15 minutes, that appears to be right at about, I'm going to say, who knows, maybe like 3.3, they would say. So they say, okay, I got 3.3 times 10 to the third meters, they say. And then they say, okay, and then that time is 15 minutes, and they say, oh gosh, I have to turn 15 minutes into seconds, and they say, no worries, I can do it nice and quick, and they say, okay, that's going to be 900 seconds, so they do that math really quick, and it's all looking good to them, and then they plug it into their calculators, and they get an average velocity that is completely the wrong number. Okay, check this equation. V average is equal to delta x all over delta t. If you are finding an instantaneous velocity, a velocity is always a change in position over a change in time. Notice these deltas here. It's always a change in position over a change in time. It is not what you have right here, which is a position over a time. None of you, when someone asks you to find the slope in your math class, none of you say, oh, I'm just going to do slope. Yeah, for sure. Slope is equal to y over x. None of you do that, ever, because you know that's not how you find slope. No, you need a change in your y over a change in your x. So you cannot do this math. And I'm telling you this now, and please do not do it on your test, because so many students do it on their test. Please do not do x over t. You have to have a delta x over a delta t. So if you wanted to find the instantaneous velocity at 15 minutes, you would not just do the position divided by 15 minutes. That's not what you would do. No, you would find the slope of the whole section. Look at that little section. Isn't the slope of that section? Haven't we already found it? Didn't we just find it? Because isn't the slope of that section the slope between 10 minutes and 20 minutes? Isn't that the slope of the section? So we already know that the slope of the section is positive 2.3 meters per second. So what's the instantaneous velocity at 15 minutes? It's the slope at 15 minutes, and the slope, which we already found, is 2.3 meters per second. Let's try an example. Can you find the instantaneous velocity of this runner at 25 minutes? Let's take a look. I'm going to erase this work here. Okay, let's find the instantaneous velocity of this runner at 25 minutes. The first thing that you will do is you will start by writing down your knowns and unknowns. I'm going to start by saying I'm looking for my instantaneous velocity. I'm going to use a little subscript here. Oh my gosh, that left out the letter N. That means instantaneous. And I'm going to say I'm looking for the instantaneous velocity at 25 minutes. Now, the way that I normally write this, hang on, let me make a little adjustment here. Boop. The way that I normally like to write this is I like to write the instantaneous velocity at t equals 25 minutes. Which is a very long subscript. If that is too much of a subscript for you, you can say instantaneous velocity at 25. And I'm fine with that. Or 25 minutes preferably, so that you include your units there. But something like that, so that we know when we're talking about. That is what we are looking for. The way that we are going to find the instantaneous velocity at 25 minutes is, wait, I'm actually going to make this big so that you can see it. 1 second. 1 second here, is you are going to find, okay, oh gosh, this is all backwards. This is very confusing. Okay, at 25 minutes, that is right here. That is right here. So the way that we're going to do that is we're going to find the slope of this whole section here of this whole section here that corresponds to the time between 20 and 30. So if we can find the slope of this whole section, we'll know the slope at 25 minutes, and the slope at 25 minutes is the instantaneous velocity. So that's our goal. To find the slope of the whole section, then, I'm going to choose 2 points on that section. But first, before I do this, I always require my students to do this step of work, because when they do this step of work, they almost always get it right. And when they don't do this step of work, they often miss it, and they often try to do x over t. Do not do x over t. You're looking for a delta x over delta t. So here's what I make them do. I say, students, before you do any work, you have to say that the instantaneous velocity at 25 minutes is equal to the average velocity, which is the slope, over the interval of 20 minutes to 30 minutes. When students write down this step, then they know what to do. And so I always say you're going to start with that step. Once you do that, now we're going to find our knowns and unknowns. My initial time for this little section is 20 minutes, which I already know a nice little unit conversion will get me to, and you could show this unit conversion. Normally you would show this unit conversion. I'm not going to show it for the sake of time here, but would get you to 1,200 seconds. You would show that unit conversion once again. My final time here is 30 minutes, which again, you would actually show this unit conversion, but that's going to get me to 1,800 seconds, like that. Then I look on my graph to find my initial position and to find my final position. At 20 minutes, I look at my graph and my position is about, we said this last time, it's about 3.8 times 10 to the third meters. I include a positive sign here for direction, or I write the word forward. My final position here is at 30 minutes, and it appears to be right at about, I'm going to say 4.7-ish. So I'm going to call that positive 4. If you called it 4.8, that'd probably be fine too, but I'm going to call it 4.7 times 10 to the third meters. Okay, now I know that my instantaneous velocity at 25 seconds is going to be the slope of the line, and the slope of the line is going to be the average velocity between 20 and 30 minutes. So next, I can say, okay, well that is going to be a delta x over a delta t. And specifically here, because it's a slope, then that's going to be an x final minus an x initial all over a t final minus a t initial. Do not forget this step. After that, then I can plug in numbers. My final position is positive 4.7 times 10 to the third meters. My initial position is positive 3.8 times 10 to the third meters. All over my final time is 1,800 seconds minus 1,200 seconds. That's my initial time. Plug that into your calculator and you would get something, when you round with good sig figs in units, like positive 1.5 meters per second. That gives me both the average velocity over that little portion of the graph, but also, because that's always the velocity, that's always the slope, that also gives me the instantaneous velocity at 25 minutes. Okay, last little problem here, or last little thing that I want you to see. We have learned how to find the average velocity over an interval. We've learned how to find the instantaneous velocity over an interval. And to find the instantaneous velocity, you just find the slope of that whole little section. Now, I want you to turn in your textbook to page 74. Okay, which is not really very much turning at all, because you're already on page 75. The last thing that I want to look at together is how you can use your a graph to find the average velocity over the course of an entire journey. Take a look at page 74, and we're going to look at number 6 here. Okay, page 74, number 6. You can see up at the top, it says use the following position time graph of a squirrel running along a clothesline to answer questions 5 through 6. And question 6 asks, what is the squirrel's average velocity during the time interval between 0 seconds and 3 seconds? Okay, this time I'm going to very vaguely draw the general shape of the graph on here so that you can see it, because I want to be able to mark on it. But you're definitely going to need your actual textbook, because I'm not going to draw all the numbers here, and this is just a vague sketch of the general vibes of this problem. Okay, so it goes, and then it goes, and then it goes, maybe a little bit lower, and then it goes like this, nice and flat, and then it goes back up to the x-axis here. Okay, here's my position versus time graph for this little squirrel that is running on a little clothesline. Here's a question, is it asks, what is the squirrel's average velocity during the time interval between 0 seconds and 3 seconds? Now, if you're looking like this, like I am, here is 3 seconds and here is 0 seconds. We're looking for the average velocity between those 2 points. Well, if you want to find the average velocity between 2 points, what you can do is you can find the slope of the line joining those 2 points. Let me show you what I mean here. I'll draw it on here. So if I want to find the average velocity between 0, please don't do that. Okay, yes, I get it. The chaos is so fun, and we love it, except that it doesn't have a place here, because this is a place of peace and of learning. And so I declare that all chaos must leave, and it must be a nice clean mark here. There we go. That is lovely. Okay, if I wanted to find the average velocity between 0 seconds and 3 seconds, I could create a little line like this, pretend that's nice and straight, a little line segment between 0 seconds and 3 seconds, and the slope of this line segment would give me the average velocity between these 2 points. So in this case, what I would do is I would create a little line segment here, and then once I create that little line segment, if I can find the slope of that little guy, then I would have the average velocity between those 2 points. Now, to do this, once again, you're going to need to write all of your knowns and unknowns. So I'm going to say my initial time here, I'm going to choose this point and this point to find the slope of my line. It's the points that were already given to me. It makes it nice and easy. My initial time here is 0 seconds. My final time here is 3 seconds. My initial position is going to make it so easy here. My initial position is equal to 0 meters. Hard to have a direction on 0, so if you just label it as 0, that's totally fine. My final position here is going to be, from my graph, it appears negative 2.0 meters. And I am looking for my average velocity between those 2 points. The way that I do it is I say, well, the average velocity is going to be the slope of the little line that I created. That's going to be a little delta x, a little rise over a little run, just like this. That rise is going to be an x final minus an x initial, all over a t final minus a t initial. That's my little run. My x final is negative 2.0 meters. And my x initial is going to be minus 0.0 meters. My final time is 3.0 seconds minus my initial time is 0.0 seconds. And here the math becomes quite easy because your zeros just kind of go away, and so I end up with 2/3. And you know that 2/3 is best represented by negative 0.67 meters per second. Hey, stop here. My answer is negative. That negative indicates a direction, which means for most of this time, or on average during this time, on average the squirrel is moving backwards. So notice, anytime my slopes are positive, that means the squirrel is moving forwards. Anytime my slope is negative, that means that the squirrel is moving backwards. And so because I ended up with a negative number here, that means for most of the time the squirrel was actually moving backwards. The last thing that I want us to look at for today is I want us to look at graph interpretation. Also, I just realized that on that graph, that sketch of the graph I just drew, I didn't label my axes at all, which you would literally never ever do because that's a terrible thing to do. But the last thing that I want to look at here is graph interpretation, and I want us to kind of get a sense for what each of these graphs kind of means. The reason why we love motion graphs in physics is because a graph tells a story. It doesn't just say, here are some numbers and here's a nice function, which is all good and wonderful, and that's why we love math. But it actually tells a story about something that happened to something. So if I have a position versus time graph here, and the shape of that graph looks a certain way, that tells me a certain something. For example, if I had a graph that looks like this, that is showing me something. The slope is constant and positive. This to me tells me that an object is moving forward because the slope is positive at a constant speed. Notice, as time goes on, my displacement is getting bigger and bigger and bigger. That means that this object is getting further and further and further away from the start line. Its displacement, its distance is getting bigger and bigger and bigger. So this shows something moving at a nice constant speed. Check out this one. Here I have a picture of an object. Pretend this is a straight horizontal line. Here I have a picture of an object, and this object is sitting a certain distance away from the start line. Imagine if x equals 0 is the start line. It's sitting a certain distance away from the start line, some distance x away from the start line, and it's just staying at that exact position as time goes on. This is an object that is sitting still. It's not moving because time is marching forward, and it is exactly where it is. It's not going forward, it's not going back. Notice the slope of this graph is 0. And because the slope of this graph is 0, its velocity is 0. It's not going anywhere. Here's another one. Let's try this one. Try this one. Here, before I explain it, pause the video and take a guess as to what this means. I'm assuming you paused the video because you're a great student and you love thinking through things on your own. And then you hit play and you learned, okay, here's kind of what I would be thinking if I were you. I would say, okay, here's the start line. It started in front of the start line. But then its displacement or its position is getting smaller and smaller and smaller and smaller, which says to me it's getting closer and closer and closer to the start line. Here it is at the start line, and then here it starts working back its way back behind the start line. I'm thinking that this is showing the graph of an object that is moving backwards. I know that it's moving backwards for a few other reasons. First, because the slope of this graph is a negative slope, and a negative slope means a backwards moving thing. So this thing is moving backwards. It also shows me that it's moving at a constant speed because it's a nice straight line. One last one here for you to take a look at. And you can see that these graphs would get really fun really fast. Take a look at this one. Okay, that's kind of a dramatic curve, but pretend it's nice and exponential. Here's what that would show you. If this was a nice smooth curve, you would say, okay, the slope starts out at 0, which means this thing starts with no speed. But gradually, it's covering more and more and more distance in the same amount of time as this graph gets steeper and steeper and steeper. A steeper and steeper and steeper graph means my slope is getting steeper, which means my velocity is getting bigger and bigger and bigger over time. This would show a picture of an object moving, getting faster and faster and faster over time. This graph you don't necessarily need to know yet, because this is not something we're going to be looking at until really next unit. But for today, there's a little teaser trailer for what you're going to be seeing in the next unit. And that is all for today, folks. I hope you have a wonderful rest of your day, and I hope that some of this makes sense to you. Remember, the biggest takeaway from today is that the slope of a position versus time graph gives you velocity. So you can find the velocity of an object by taking the slope of its position versus time graph. We also talked about how to calculate instantaneous slope. To find the instantaneous slope, remember, you're just looking for the slope of that interval because that will give you the slope at a very specific point. And lastly, we found that you could find the average velocity between 2 points by finding the slope of the line between those 2 points. And that is pretty much all for today, folks. I hope you have a wonderful, wonderful rest of your day, and I'll see you all next time. Bye, good people.